We'll explore how we understand and describe movement in the physical world using vectors, scalars, and related mathematics. To help visualize this, think of a compass, which shows direction clearly, much like how vectors help us represent direction and magnitude in motion. We'll break down these concepts step by step to build a strong foundation in how objects move and interact in space. Let's get started. Let's consider a situation where a Coast Guard rescue team gets a distress signal and is told it is exactly 50 kilometers away. While that number gives them a radius to search within, it doesn't tell them the exact direction or location along that radius. This means the search area forms a large circle with a 50-kilometer radius, and the rescue team has to cover that entire area, not just a single point. This example highlights that knowing just a distance isn't enough to pinpoint where help is needed. Let's look at the two main ways to describe physical quantities, scalars and vectors. Scalars are the simpler type, defined entirely by a single number along with the unit that goes with it, like meters or seconds. You can think of them just as numbers that tell you how much of something there is. Vectors, on the other hand, give you more information. They're described by a number and unit as well, but also include the direction. This means that vectors don't just tell you how much, but also where or which way something is acting, making them essential for understanding things like forces or velocity. When we look at the physical world, we can organize different quantities into two main types, scalars and vectors. Scalars are values that only have magnitude, like time, volume, mass, distance, speed, temperature, and energy. For example, time might be 50 minutes, or distance might be 100 meters, just a number with no direction. Vectors, on the other hand, include both magnitude and direction. Displacement is a vector because it tells us not only how far something has moved, but also the direction, such as 2 kilometers northeast. Other examples of vectors include velocity, acceleration, force, and torque. These all describe something's size and the direction it's going or acting. Understanding this difference helps us better describe and analyze physical phenomena. Let's take a closer look at how we represent vectors using arrows. The arrow's length shows the magnitude, which is always a positive value, and the arrow's angle shows the direction. In mathematical terms, a vector is usually written as a letter with an arrow above it, or in bold type. When writing just the magnitude, we use the same letter but without the arrow. For example, here the vector d starts at the tail, which marks the origin, and ends at the head, showing the vector's direction. The distance between the tail and the head gives us the magnitude of the vector d. This visual approach helps us easily understand both how large the vector is and the direction it points in. Now, let's look at how movements combine when they happen along the same line. If two vectors are collinear, adding them is just a matter of simple arithmetic. In the first scenario, imagine a boat moving north at 6 knots and then the current pushing north at 3 knots. Combining these, the boat's overall speed becomes 9 knots north. In the second scenario, the boat still moves north at 6 knots, but now the current moves south at 3 knots, acting against it. So, the resulting speed is 3 knots north, which is the difference between the two. This shows how adding or subtracting vectors along the same direction affects the total movement. Let's continue by looking at the geometric approach to adding vectors in 2 dimensions. When you add 2 coplanar vectors, you place the tail of the second vector at the head of the first one. The resultant vector is then drawn from the starting point of the first vector's tail to the endpoint of the second vector's head. For example, starting at point A, you can go to point C along vector d_AC. Then from point C to point B along vector d_carbon monoboride. The overall movement from point A directly to point B is represented by the resultant vector d_AB. This method helps visualize how vectors combine to produce a final displacement or direction. While drawing to scale can be very effective for simple problems, as the complexity increases, it becomes much harder to maintain accuracy. When dealing with multiple legs in a journey or several forces at once, you need precise tools like rulers and protractors, and even then, small mistakes can easily add up. This kind of manual approach leaves room for human error, making it less reliable for complex scenarios where precise calculation is critical. Here, we see how any vector can be broken down into two parts that are perpendicular to each other, one along the x-axis and the other along the y-axis. This means instead of dealing with the vector as a whole, we can think of it as the sum of these two simpler components. The vector A is shown as the diagonal of a right-angled triangle, with its horizontal part labeled as A_x along the east direction, and its vertical part labeled as A_y pointing north. By doing this, it becomes much easier to analyze and work with vectors in terms of their x and y components, without needing to draw the triangles every time. Moving on, let's continue with the trigonometric approach to breaking down a vector into its components. By measuring the angle theta counterclockwise from the positive x-axis, we can use basic sine and cosine functions to find the exact lengths of the horizontal and vertical parts. The horizontal component is found by multiplying the length of the vector, A, by the cosine of theta, while the vertical component is the length of the vector times the sine of theta. This method ensures we have precise values for both components, which makes calculations and further analysis straightforward. Let's take a moment to summarize a simple but powerful approach to adding vectors. Instead of trying to combine vectors directly, you break each vector into its components along the x and y axes. Then, you add all the x components together to find the total x component of the result, and do the same for the y components to get the total y component. This way, the combined vector, or resultant vector, is found by adding the corresponding components together. This method works for any number of vectors, and even extends nicely into 3 dimensions by including the z components. It's a straightforward way to handle vector addition without getting tangled up in geometry. Now that we have the final x and y components of the vector, we combine them to find the overall magnitude and direction. To get the magnitude, we use the Pythagorean theorem, which means taking the square root of the sum of the squares of the x and y parts. For the direction, we calculate the angle by taking the inverse tangent of the ratio of the y component over the x component. This gives us the angle the resultant vector makes with the x-axis, completing the process of rebuilding the vector from its components. Here, we see an ice hockey puck being struck by 2 sticks at the same time, with forces acting along 2 different directions, the x-axis and the y-axis. The force along the x-axis is 30 newtons, and along the y-axis, it's 40 newtons. To find the net force on the puck, we combine these 2 forces as vector components. The result is a net force vector with a magnitude of 50 newtons, calculated using the Pythagorean theorem. The direction of this net force is about 53.1 degrees from the x-axis, which we find by taking the inverse tangent of the ratio between the forces on the y and x-axes. This example shows how we can calculate the combined effect of forces acting at right angles in a practical, real-world situation. Let's move on and highlight 2 common misunderstandings involving vectors. First, the magnitude of a vector can never be negative because it represents a physical length, which by nature is always positive. When you see a minus sign, it just shows that the vector is pointing in the opposite direction, not that its length is less than 0. Second, you cannot add a scalar directly to a vector. For example, adding a time duration like 50 minutes to a displacement such as 20 kilometers north doesn't make sense mathematically because they represent different kinds of quantities. This operation is undefined because they aren't compatible units, so this kind of addition isn't allowed. These points are important to keep in mind to avoid confusion in calculations involving vectors. Now that we have all the tools laid out, this summary helps us see how to break down a vector into its components along the x and y axes by using the cosine and sine of the angle it makes with the horizontal. We can then use these components to reconstruct the original vector's magnitude and direction through the Pythagorean theorem and inverse tangent function. Finally, when we're working with multiple vectors, the analytical addition rule tells us to add all the individual x components and y components separately to get the resultant vector. This toolkit simplifies moving between physical measurements and mathematical expressions, making it easier to analyze and solve problems involving forces or velocities. Understanding the direction of a force or movement is crucial in many fields, from piloting rescue drones through severe weather to engineering safe bridges and accurately predicting planetary orbits. Quantifying an effect isn't enough on its own. Knowing which way something is going or how it's oriented makes all the difference. This insight helps us make better decisions, avoid errors, and create solutions that work reliably in the real world.